Okay, so welcome back. Now, in this video, we're going to start talking about the integral test. Okay, so in previous videos, we talked about the harmonic series and we showed how the harmonic series diverges. So we're going to, again, use the harmonic series as a way to also show how the integral test works, because one of the things about the integral test is it can be used for many different series to show whether that series converges or diverges. So we're going to use the integral test to show, again, that the harmonic series is a divergent series. Okay, so here's the situation we have here. So I'm going to set it up. So we've got the harmonic series, and last time we looked at the partial sums, right? We looked at the partial sums, the sequence of partial sums, to show that the harmonic series diverges. So now what we're going to do is we're going to look at this setup, okay? And so this technique is important because, one, it's used to prove divergence or convergence of many of the many series. Now the integral test, what we do is we compare an infinite sum to an improper integral. Okay, so it's important to note that this test can only be applied, so here's one of the things you have to keep in mind. It's only can be applied when you're considering a series whose terms are all positive. Okay, so that's the first thing you have to check, is make sure that all of the terms are positive. So in this case, the harmonic series definitely satisfies that condition. Okay, so now what we're going to do is I drew out this graph. So let me do it this way. So each rectangle represents one of these terms, right? So the area of the rectangle corresponds to an n value. So n equals 1 represents 1. So that's the first term. And so the area of this is 1, and then here the area of this is 1/2, and then 1/3, and then 1/4, and so on. Okay, so because what we're going to do is we're going to compare it to the area under the curve, right? So now you can see from this picture that the area, or the sum, the partial sum, if you will, is larger than the curve, right? Because we're using n equals 1, and so all of our rectangles are slightly overestimating the area under the curve, right? So this is an overestimate, okay? So now, let's look at this. So here's our series, the harmonic series, and so here's an example of our partial sum, right? So the partial sum is given by this, which is given by this sum. And so we know that this sum, this partial sum, is greater than the area under the graph 1/x. Okay? So we're going to compare the areas, right? That's basically what we're doing. So we can see that this area is always going to be bigger than this integral. Okay, so what does that mean? Well, that means S sub k, which is equal to n equals 1 to k of 1/n, is always going to be bigger than, again, the integral from 1 to k plus 1. Why k plus 1? Well, the rectangles start at n equals 1, n equals 2 represents this rectangle, n equals 3 represents this one, until you get to, let's say, 5. Let's say the last rectangle. Well, in order to have the curve 1/x go out far enough to capture this rectangle, we would have to go to k plus 1, okay? Not k. So that's why we have k plus 1 here. Okay, so now it's going to be 1/x dx, Now what this is equal to is obviously you integrate this, and this is going to be the natural log of what? The absolute value of x evaluated from 1 to k plus 1. And of course, this is going to equal the natural log of the absolute value of k plus 1 minus the natural log of the absolute value of 1, right, which we don't need, right, the absolute values, so it's just going to be the natural log of 1. Okay, now, what's the natural log of 1? Well, the natural log of 1 is 0, right? So then we just end up with the natural log of the absolute value of k plus 1. Now, well, that's interesting. So what do we do with that? Well, now all we have to do is we take the limit, right? So we're going to take the limit as k approaches infinity. Well, what happens to this as k goes to infinity? Well, as k approaches infinity, the limit, the natural log of the absolute value of k plus 1, okay? We could drop the, we could drop the absolute values because k is always positive, so the natural log of k plus 1 goes to infinity, right? Now, since the limit of the natural log of k plus 1 equals infinity, therefore doesn't exist, we see that the sequence of partial sums is unbounded, right? So the integral is going off to infinity, right? So let's write it more appropriately. So let's use limits. So the limit as x goes to, k. Yeah, the limit as k goes to infinity of the natural log of k plus 1 equals positive infinity. So since this area, right, so think about it, since the area under this curve is going off to infinity, and the sequence of partial sums, right, the partial sums are always greater than the corresponding integral, then this tells us that the sequence of partial sums is unbounded, right? And since the sequence is unbounded, guess what? It does not converge. It is divergent, or it's a well, that's it. It diverges, and consequently, the series also diverges. And that's the answer. Okay. So now. Now let's consider another one. Well, you know what? I'll come back and we'll do that one. So we'll consider another example where it does converge. See you then.